Today's lecture is about the physics in Unity. Our goal is going to take a brief overview of the physics engines that are available in Unity, the components that are involved, and what we can do with that physics engine. So first of all, you need to know that there are two separate physics engines. Separate is a key word here. There's one that's dedicated to work in 3D and the other one for 2D. They're implemented using different components. They're similar in many ways, like for example, you get a rigid body for a 3D physics and a rigid body 2D for the 2D physics engine. So there's similarities in the way because they are rigid bodies and they're going to have similar properties, but they will not interact with each other. So that's why separate is a keyword. You cannot mix and match. So you could not use a sprite with a 2D rigid body and a 3D collider. You're going to have some issues when it comes to handling interactions with other objects. So make sure whenever you set your projects, do not mix 2D and 3D. Rigid body is basically going to be the component that's going to allow you to enable physical behavior using that physics engine for your game object. If your game object has a rigid body, then you should use that rigid body to move the object. You can use forces. There are other methods as well to move a rigid body. Those are the ones that you should use. If you're not going to want to use the physics engine for controlling the motion, then in that case, you're going to set the rigid body to kinematic. In that case, it will allow you to detect some of the interactions, and it will not be controlled by the physics engine when it comes to bouncing or items of that feature there. So something to keep in mind. We're going to take a look at the features for rigid bodies. This is maybe an older screenshot, but it includes most of the features that a rigid body has, even with newer versions of Unity. So you can add a component physics rigid body. It will have a lot of features there, like the mass, the drag, the angular drag, whether it uses gravity or not. If you choose to use kinematic, is kinematic or not. So again, is kinematic, we'll talk about that in just a moment. But that's if you do not want to have the bouncing type aspect of collisions. You don't want to respond to the push of forces and things like that. So let's go ahead and dive into these features and how you can use them to get the appropriate behaviors in your game. The mass is basically going to be the mass of an object. By default, it's meant to be in kilograms, but you do want to use numbers, and that's what you want to keep in mind, that are kind of like in proportions. So if you have like a big object that's supposed to be pretty sturdy, you want to set the mass to be much higher than if you have like a little bouncy ball that's going to be a lot lighter. So even though by default we're considering it to be kilogram, really it's not really what matters. What really matters is that you set the proportions of the weights of your different object proportionally. The drag is basically, whether it's the drag or angular drag, it's the resistance. So let's say you're using the rigid body and you're using physics forces to push them, and you have something that's pretty light, it's going to move pretty fast. And if you want, when there's no longer input, you want them to slow it down, then the drag is where you're going to be able to do that. It's going to basically apply some resistance against the forces that are applied to the object already. So it'll slow it down. It kind of simulates friction. You would, for example, if your objects are moving in the air, you would set up a drag that would be much less than if your objects were meant to be in the water. The angular drag is pretty much the same thing, but it's applied for rotation when the objects are spinning. Gravity is whether you're going to use gravity or not for your game objects. It's just a yes or no kind of question. Is kinematic, again, is when you want to ignore physics forces. So you don't want to, if your object hits something, you don't want them to bounce or anything like that. So that's what is kinematic. Is going to be still useful if you want to deal with interactions, like your trigger events, but it won't respond to physics interactions. Interpolate, you may want to change those settings if you are seeing some jerkiness in the movement of the rigid body. For collision detection here, you may want to alter these if you have objects that are moving really fast and they may be going through other objects without detecting collisions. That's when you want to modify that setting. And the constraints are basically going to be restrictions to the motion of the rigid body. So you can prevent some movement along certain axes. Let's say you want your objects to stay on a plane, you can prevent its up and down coordinate to stay the same. So depending on how you set it up, it should be the y coordinate. But you could say freeze on the y coordinate and your object would not fly up in the air, for example. So the interpolate property, again, I said if you notice some jerkiness in the movement of your rigid body, that might be something you want to look into and try out. By default, it's set to none, so there's no interpolation. There's also the interpolate and extrapolate, and that basically is an effort to smooth the transform based on the previous frame with the interpolate and the next frame with the extrapolate. So if you see some jerkiness in the movement of your rigid body object, then go ahead and try to modify these, see if it helps. Collision detection property is, again, that's if you're noticing that some of your collisions are not being detected properly. Chances are it's because your object may be small and moving in too fast. So if you choose discrete, which I believe is the default, it will detect the collisions against all other colliders in the scene, and for normal collisions that's what should be used. Continuous is a little bit more strenuous when it comes to calculations, but it will detect detection against dynamic colliders. Those are colliders that are also associated with a rigid body. And then it will use continuous detection against the static ones, the ones that are meant to be still in your scene. Continuous dynamic, this is doing continuous detection for all objects. So if you have something that moves really fast, this is maybe the one that you need to use. However, be careful, because when it comes to calculations, it's more demanding. Colliders, you're already familiar with the concept. You need to have colliders for your game objects in your scenes, otherwise it's like they're not there. There are several colliders that are available, whether you're dealing with 2D or 3D, it's the same, similar concept, I should say. So by default, you get to have the box, the sphere, the capsule. There's also mesh, wheel, and terrain that we'll talk a little bit later. The primitive ones are going to be the box, the sphere, and the capsules. They should be your top priority. You can add more than one if you wanted to. If you have an object that has a complex shape, you can set up 2 or 3 or more to represent the shape of your object the best. The advantage of those primitive colliders is they are keeping the processing calculations, they're keeping that low. So you can use that easily to approximate the shape of your object and reduce the calculations at runtime. While you can have multiple primitive colliders on your objects, there should only be one rigid body. Make sure that each object that you have only has one rigid body. That means also including with the children. Some of the collider properties that you can change, there's the edit collider. That's if you need to kind of alter the shape a little bit of your collider. You can click on this button and go ahead and change the vertices and kind of resize the size of your collider. Whether the collider is triggered or not, and we'll see what that impacts in a little bit. You could decide to apply a physics material We'll take a look at those in a little bit, but you can apply some characteristics to your collider that will make your object appear more bouncy, or that will appear less bouncy, like if they had different types of materials like wood, rubber, etc. You can alter the center and the size of your collider in order to make it match the shape. You're probably already familiar with this. There are two types of colliders really when you're dealing, and mainly I'm talking about 3D, but that can be applied to 2D as well. We'll talk about 2D some later on, not in this lecture though. Colliders can be added to your objects that do not have rigid bodies. Like if you have floors or walls, they don't really have to have any physics forces applied to them. And so anything that's motionless in your scene, you can just put some colliders on them and not add any rigid bodies. They will be considered your static colliders. They will not respond to physics forces in any way. If you have a collider on an object that already has a rigid body component, or that you're going to have a rigid component on, a rigid body component, then those are going to be considered your dynamic colliders. Those are the ones that are going to be able to generate events with your collision, enter, exit, and all that. We'll talk about that in a minute. Physics material, I mentioned it briefly. You can find some. There's standard assets. They might be a little outdated now, but they have some materials that are already created. It's really simple to create your own, and the idea is to kind of make an object appear to be either bouncy or slippery or whatever case may be, depending on what you need. So that's the whole purpose of the physics material. You can see you can alter friction. So if you wanted to do something slippery, for example, you would set that friction to something like 0. Those values are between 0 and 1. And then the bounciness is the same thing when an object hits something else. How much of that force that it came and hit it with, how much of that force is going to be used to send it in the opposite direction. So 0 would mean you're not bouncing at all. 1 means you're bouncing back 100%. The friction, combine, and bounce, there's other settings. I'm not really going to get into that. If you're interested, go ahead and check the documentation. So we talked about colliders being trigger or not. Trigger colliders are going to detect interactions or collisions, but the object is going to go through, unless you have another collider, obviously. The interactions can be detected using the on-trigger enter, on-trigger stay, and on-trigger exit. These are events, just kind of like your start, awake. They're called automatically whenever there is a collision with a trigger collider. When you are using these methods, you can write your code to determine what happens. Oftentimes, it's great to use that for a pickup. If you collide with an object, if your player has a rigid body and collides with an object that has a trigger collider, it will kind of look like it goes through it, but as you go through it, the on-trigger enter, on-trigger stay, and on-trigger exit will be called, and you can do what you need to do with the pickup, destroy it, add to the inventory, whatever else needs to happen there. So let's go ahead and take a look at a project in Unity. I have in here several items, and I tried to open that up so we would save a little bit of time there. So I have in my scene a green cube. As you can see, this is what will be called a static object or a static collider. It's just a plain cube. It's green, and it has a box collider on it. Note that that object is a trigger object. That means that I check the is trigger on its collider. That's pretty much it. I have a player. Note that the player does have a rigid body. It has a sphere collider. That's an actual collider, not a trigger. And it's got a player controller script that I'm going to go over in a minute. And then the last object is another cube that is blue. This one is pretty much static as well, but it is not trigger. and then it's got like a different tag there. So basically that's all I have in the scene. I have opened up my player controller script to show you what it has. Basically the movement is handled, you're using the X and Y axis inputs, so your left arrow keys, up and down keys, or the WASD. And then I use this for moving my object along the X and the Z axis and add the force to the rigid body. That's one quick and easy way. It's kind of like a rollerball. I don't know if you've ever done that, but it's pretty much the same. Note that I get access to the rigid body component here in the start, and then I apply a force in the update as I gather input from the players. And note that because I'm dealing with adding forces, then I should use the fixed update. The fixed update should only be used for physics calculations. It's kind of taxing to a certain extent, so make sure you save this only for physics behaviors. And after that I have trigger enter, trigger exit, collision enter, and collision exit. I didn't use the stay ones. Basically what I'm doing is in the start I get the initial color of my object, my player. When I enter a collision with the trigger cube, which is the green cube, they're all tagged the coloring cube by the way, then I'm changing the color to the color of the cube. When I exit, I go back to my initial color. Same thing with the collision event. When I hit or I enter a collision with the blue cube that is not set to trigger, then I'm going to get the color of the blue cube, and when I exit that collision, I'll go back to my original color. So nothing too complicated there, but it's just to show you the difference between trigger and not trigger. So if I were to press play now and show you how this works, my player moves as expected. If I enter the collision here, I'm going to go slowly on purpose, I turn green, and on trigger exit I turn red. Note that I actually go through the object because it's trigger, and when I exit it turns back red. When I get into the collision with the blue cube though, you can see briefly I turned blue and I went back red. I bounced off of it. Note that if I look at the blue cube, it's just a static, so this one will not move at all. It will interact with the player. But if I stay on collision, like stuck on its side, I stay blue, and when I exit, I leave. But I cannot go through that blue cube there. I could take a look at adding a rigid body to the blue cube. So if I were to add a rigid body to the blue cube, I'm going to keep them both with the same mass of 1. Now if I hit the blue cube, you can see I can actually move the blue cube. What I could do is, if you see my player right now, the mass is 1 and my blue cube has the same mass of 1. Obviously it should be heavier, so maybe I'm going to set its mass to 5 because it's a little bit bigger. If I do that in my interaction, it'll be a lot harder for my player to move the blue cube. You see it moves a little bit, but not as much. And you can use these values there to kind of set up the behaviors that you want. One thing that I did not talk too much about is when I deal with my player there. Let me remove this component rigid body for a second because I just want to deal with the player right now. So the drag right now is set to 0. What if I set, and I wanted to show you, I'm going to press play. I'm going to press to the right and let it go. It takes a little while for my player to stop moving. So if I were to change its drag to maybe 2 and press play, I'm going to try to use similar motion here to the right. But you can see it doesn't keep going like it did before. So the drag is really good to control that kind of behavior if you don't want your object to keep on rolling. Now if you put your drag to be a little too high, let's say I were to put it to 20 because I really want it to stop right away, you can see when I press play I'm having a hard time to move my object. I'm keep on pressing the left key here. It's not going very far. So if that's something you want to do, have a strong drag, you may need to go ahead and increase the speed of your object. Like my speed was 10 here, maybe I can put it to 20, just as an example, to see if I can actually move my player. So it moves a little bit better, but you can see I'm struggling because I'm trying to overcome the drag. So in that case, you may want to increase the speed a little bit more, but you get the idea. Alright, let's go back to the PowerPoint. I can skip that. So with the collisions there, on the first physics update, where the collision is detected, on collision enter is called. Then where contact is maintained, it's collision stay, and exit is when the contact has been broken. One of the object has to have a rigid body, like my player did, and it cannot be kinematic. So it's non-kinematic and it has to be a rigid body. The other one can just be a plain static collider, that's fine. But one of the two objects has to have a non-kinematic rigid body. Here is a matrix that's going to show you basically when you can expect collision or not. So on the left side, you can pick your first object and what kind of collider and rigid body it has. And at the top, that would be your second object, for example. So you can see, let's say I have a static collider. That would be the same thing as my blue cube originally. No rigid body, nothing, just a static collider. It will only detect a collision event on collision enter, etc., with a rigid body collider. So that's kind of how it matches here with the intersection. So that's the only situation for a static collider to have a collision being detected, is if it enters in contact with an object that has a rigid body and a collider. No triggers there. The static collider can also generate trigger events if you have a rigid body with a trigger collider, or if you have a kinematic rigid body with a trigger collider. So you can see overall that it's going to be a lot easier to have trigger events being generated than non-trigger events. You can go ahead and every time you're experimenting in your game and have objects interacting and using collisions versus triggers, refer back to this chart if your events are not being called as expected. Check out what components does the first object have, what components does the second object have, and then see if, according to this chart, they should have an interaction or not. Oftentimes, this is the main reason why students encounter issues with their collisions. There is, and I believe there's the assets now that are available that are already pre-programmed for you in the Unity Asset Store, but you can use something called a character controller. And basically, it gives your character a capsule-shaped collider. It's always upright, but you can change that if you wanted to. There is no need for a rigid body. It's kind of like included. A character controller cannot walk through static colliders, so it'll bump up of things. It can push rigid body objects aside as well. The character controller will not be accelerated by incoming collision. So if something comes and hits it, it's not going to be accelerated with that. Alright, so that's a note. Sometimes character controllers are a little bit easier to deal with than rigid bodies. So if that's something of interest, you should investigate it further. Something that I wanted to bring to your attention is what's called the layer-based collision detection. Layer-based collision detection is a way to make a game object collide with another game object that is set up to a specific layer or layers. You can just use the layer drop down at the top of the inspector window and assign a different layer to different objects. Under Edit, Project Settings, Physics, you can see there's going to be a collision matrix that will determine which layers interact with which other layers. This is what that matrix looks like. So this is under the physics manager. You can see the different layers that are existing. So you have the default layers. They're showing in all directions. So they're showing horizontally and vertically as well. There's the default layer. These are some layers that already exist. And then you can have your custom layers as well. And then you can, if they have a check, that means that they will collide. And if that's deselected, it will not. There will not be any collisions. Before I move into raycasting, I wanted to show you an example of that. So in this project here, and I should probably show you the Unity scene here, I have a bunch of green spheres and a bunch of blue spheres, and all of them are pretty much the same. They have this script that moves them automatically. They all have a collider, a true collider, no triggers, and they have a rigid body as well. Same thing with the blue spheres. They're all pretty much set up the same. They are not trigger colliders. They're regular colliders, and they have rigid bodies. I do have a player that is moved in the same way that I used the previous scene there, like a rollerball type thing. And I do have some walls there set up. Those are just static colliders, no rigid bodies involved. So what I did is for all of these objects, I moved them randomly with forces. Nothing interesting there. It's kind of a not that great code anyway. But every time I enter a collision, I write that there is a collision that has been detected. In my game, really, what I'm interested in is seeing how my player interacts with the blue or the green spheres. I am not interested in detecting collisions between the blue spheres and the green spheres. I really don't care about that. So first of all, let's go ahead and take a look at playing the game for a few seconds. And I'm going to move my player around. I'm going to show you a little bit by just playing for a few seconds. You can see everything is bouncing off of everything else. And after just a few seconds of playing, I already have 527 messages that display collision detected. It's not that bad though. But I really don't need all of these collisions. So what I did, and I already created there, under the layers, I added the layer for my player, for the green spheres, for the blue spheres, and for the walls. I created the layer for every single one of them, and I'm going to assign them at this time. So I'm selecting the parent objects. These are just empty objects, but I can assign that to I have the green spheres right now, so I can assign the layer to this and then change the children. So it's not necessarily going to impact the parent, because it's not going to generate any collisions, but it will impact all of the children there. I'm going to do the same thing for the blue spheres, put them on their own layer, and then I'm going to change the walls, put them on the walls, change the children, and the player, I'm going to put it on the player level, or the player layer, sorry. There it goes. So I've set up my interactions there. I haven't changed anything. They're just in different layers. So if I were to press this again and move around the scene, I can see after just a few seconds I get a lot of events being detected, because there's a lot of blue and green spheres there. So far that's good. Let's go ahead and see what happens into the physics manager. So I can go under the project settings here, and I've already selected the physics. So you can see here, I forgot to check this one back. You can see right now everything is interacting with everything else. What if I decided, well, the player needs to interact with the walls, it needs to interact with the blue spheres and the green spheres, so that's great. I only have one player in my scene, so whether this is selected or not doesn't really matter. If you had multiple players and you wanted them to interact, you probably would leave that checked, so I'm going to leave it alone. The green spheres, well, I could say I don't really care if they hit the walls or not, so let's deselect that. That might be a mistake, but we'll see that in a minute. They definitely don't need to interact with the green spheres, and they don't need to interact with each other either, so that's fine. The blue spheres, they don't need to interact with the walls, or so I think. That might be a mistake. And then the blue spheres don't need to interact with each other, so I can deselect that. That's great. So my player is going to interact with all of them, but they don't interact with each other, they don't interact with the walls. The walls are not going to be moving, so that doesn't matter. I can leave it as it is. Let's go ahead and see what happens now. When I press play, my interactions are gone, but because I don't allow the blue spheres and the green spheres to interact with the walls, well, they kind of go through them. So that was definitely a mistake. Let's go back and fix that. You want to make sure they can interact with the walls so that they don't leave the area, unless that's something that you want to happen. But in my case, that's not what I want. So now when I press play, they should all remain in the scene there. You can see though that the collisions detected are a lot fewer there. I played longer already, and I only have like 180 collisions there that are being detected. So by just going under Edit and Project Settings and disabling interactions between the blue and the green spheres, my interactions are going down quite a lot. Ideally, and this is another thing, when it comes to coding, it probably would make more sense to handle the collisions with the players, because those are the ones that actually matter. But my purpose here was to show you that just by setting up a layer and checking how many collisions were detected, it would kind of make it more efficient. Note that the collision enter is going to be looked for even if you don't have an event there. So make sure that you only set up the onCollision enter for objects that will interact, and ideally you would set that up on your player so that it makes a lot more sense in your interactions anyway. Alright, let's go back to the PowerPoint. We're going to discuss raycasting. Basically with raycasting, you're sending out an imaginary ray, and when you send it out, you see what it hits. It's great for things like aiming, finding the line of sight, gauging the distance, determining if there's something nearby. The raycast method has a lot of overloaded methods, so you can use the raycast with a lot of different arguments when you're calling that method. So here's an example. You can cast a ray against the colliders in the scene and then return information on what was hit. So if you're looking for trying to find out what's in a specific direction for a specific distance and find out what's there, then you can use the raycast, where you're using the starting position, the direction, and how far. So in my case here, I don't really care what I hit. So for example, I have a character that needs to move left, right, forward, and back, and I just need to see if there is something in front of them before I move them. So in that case, I cast a ray in the direction of forward, in a short distance, because my player is just going to do one step in that direction. And if I find something, I don't care what it is. It means I can't move. There's something in front of my object. So in that case, maybe you would use if not physics raycasts, etc., then move the object. That would be a good use for that method there. You don't really care about what was hit in this implementation there. You can get information about what was hit in a different way, but right here I don't really care what I hit. All I want to know is whether I can go in that direction or not. That works out very nicely. Now oftentimes you will need to have information on what was hit. Maybe you're trying to figure out if it's just a wall or if it's an enemy. Now this would be better if you were trying to do something, to act upon the object that's in that specific direction. So here we're using the direction of up. Maybe we're trying to shoot like things that are flying over our head. I'm not sure. So you have to declare in that case a raycast hit variable. Oftentimes it will call hit or hit info. Those are like typical word names for that variable. And then your physics.raycast, you're going to specify, actually I'm shooting down here. So for example, if you're like using this for jumping, maybe that could be useful. That's starting from the position of the player, transform that position. Negative vector 3.up, that means it's actually going down. And then for out, I get the variable hit. So if the raycast is successful, hit will have a value inside of that if statement. Outside of that if statement, hit will be null. So and then you can get information about the hit, so you can use hit.distance, that'll tell you how far the object is. You can get hit.gameObject, that'll tell you what game object was a hit, etc., etc. Another use here is pretty much similar to the previous one, but you set up a maximum distance. You do want to be conscious of the raycast because it can be excessive, especially if you're doing it in the update. That would be excessive use of your raycast, and so you may want to set a maximum distance. You don't want to shoot your ray till infinity. Sort of, it wouldn't go to infinity, but you don't want to cast a ray too far. So you can still use it starting from the position of the player, going into negative vector 3 dot up, so that means down. You could still get information about a hit with that raycast hit variable. And then you set up a maximum distance there. So sometimes that maximum distance, if you set it to be too short, you may not detect collisions. But you do want to find kind of like your value that works very well without being too excessive. And here you would get the access to the distance as well if you wanted to. Sometimes, and that happens quite a lot in games, your raycast is not working as expected. It could be because your distance is not far enough. It could also be because you're not going in the right direction. And because raycasting is invisible, it makes it kind of hard to figure out what's going on. So you can actually draw a line between the point that you started and the point where it ended. For example, if I do a transform.position vector 3 forward, that will go and draw a line between those two items. The color is whatever color you want to use for the line that will be drawn. And then the 2 is the amount of time you want that line to be drawn so that you can actually see which direction it's going. A little note here, you will not see this in the game view, you will see that in the scene view. But it can be really useful to see if you're shooting in the right direction, if you're shooting... now here, a little note. If I were to use it to debug, I guess it wouldn't be that situation, it would be this one. I'm trying to see if why my raycast is not shooting or not returning any values. Note that here you're starting from the transform.position and forward, and your distance is 10. If I were to draw a line with transform.position and vector 3.forward, it will only move to the length of the vector 3.forward, which is 1. So if you wanted to make your line longer, you would have to do vector 3.forward times 10 to make it go to the same distance as your raycast. Alright, let's go ahead and take a look at some raycasting examples. So for this example here, I have created a scene with some spheres in it. You can see the spheres are pretty simple. They were static and they have a collider on them. They're not even tagged or anything. Then I have a sphere, another one. So all those spheres have the exact same values here. What I'm going to do is I'm going to switch my layout to 2x3 so I can see both the scene view and there it goes. I want to be able to see the scene view and game view at the same time because I believe I've got some draw lines there set up. Let's go ahead and take a look at the script. So I believe I added this script to my camera. Not necessarily a great thing to do, but it's fine for this example there. And basically I'm trying to identify with the mouse, I'm moving or rotating the camera. So you can see if I press play and I move the mouse, I'm actually rotating the camera. It may not be, I may be a little dizzying, and you can see I'm destroying spheres, but I haven't gone over this yet. So I'm moving the camera or rotating the camera with the motion of the mouse. And then I'm calling this method, which is called the destroy sphere insight. Basically what I'm doing is I'm shooting a ray, physics.raycast, from the transformed out position of my camera. I'm doing it in a forward position. I'm getting access to the information that Raycast hit there, whatever I hit, and I'm going in the distance of 20. And if I actually hit something, I just destroy them. That's how the spheres get to be destroyed. Note that I'm drawing a line here from the transformed out position to the transformed out forward, and really, to be honest, I should use 20 here to match exactly what my Raycast is doing. So, and that could actually that could be a good thing to do to determine how far you should see. So if I'm going to press play here, you can see the Raycast and where it's going. As I rotate, you can see the distance, and it may be a little harder to see whenever I have to get them exactly straight in front of me before I destroy them. So I've got to try to place them right in the middle. There it goes. And you can see the Raycast. You may notice, if I wanted to actually maybe get a little better idea of what's happening with my Raycast here. That 20 shows me I'm shooting a little bit too far there. Maybe a 10 would be better. So we can go ahead and alter this distance there, make it just a 10, and make sure I look at it also. I change my draw line to kind of match the same distance there. So if I save my script and run it, and that's kind of the advantage here of the draw line. I can see a 10 should be plenty if I can place the spheres in the middle. Well, actually, it doesn't look like it's enough. I'm pretty much sure I had them. So even though the debug.drawLine looks like it's going far enough, I'm not reaching the sphere there. So I guess in a way that doesn't really prove my point. The 20 was better. So it's not exactly a one-on-one kind of a match, but it gives you a good idea of the direction at least. Let's go ahead and try to run this with 20 in the distance. It's kind of interesting the way it looks like it worked, but it didn't. There we go, now it works again. So make sure you adjust these settings there to kind of have them match your game so it still functions. And then we just saw there's not necessarily a one-on-one correlation between that distance and the distance that we have for the Raycast here, but at least it gives you a good idea if you're going in the right direction or not. Alright, let's finish up here. So here are some of the things that you should consider when dealing with the physics engine. Number one, you should define different layers for your types of objects and limit the interactions with the collision matrix. That's kind of what I showed with the green balls and the blue balls. If they don't really need to interact with each other, then cancel those interactions. Now, if you do need to have them bounce off of each other, that's a different story. But if you don't, then you may want to consider setting up layers and reducing your interactions. So for example, there's there was somebody that did the experiment. I didn't do it, but it was similar to what I had there. Instead of having 5 or 6 or 10 red and green objects or blue and green objects, they had 1,000, and they were all inside of box containers, and then they were all being able to interact with each other. So after 5 seconds, 53,624 collisions were detected. Then they decided to place the green and the red objects on separate layers, like I did with my blue and green objects. And then they decided to not have them interact. And you can see the number of collisions was still pretty high because they were hitting the edges of the box there. But it reduces quite a lot to 29,171 in 5 seconds. that's not neglectable. And if you are using things like mesh colliders, that definitely should be a consideration, because mesh colliders compared to primitive colliders are going to be a lot more intensive when it comes to those physics calculations. When you're using raycasting, try to keep the length of your ray to what you need. Don't use the raycast without specifying a maximum distance, and when you do, make sure that maximum distance is working for your project but is like optimal. That means you don't shoot to 1,000 when you only need to go to 100. Don't use raycasts inside the fixed update. Maybe the update might be an overkill, and a lot of things that you do, for example, if I have a player and it's moving forward and I want to make sure there's nothing in the way, well, I should only worry about it, I should only cast a ray if my player is trying to move in that direction. So I don't need to do it for every single frame. In some situations, you may be able to use a coroutine. So instead of doing it 30 to 60 times per second, maybe you only do it twice. That might be enough. So a coroutine might be better there. If you are doing raycasting against a mesh collider, that's going to be expensive. If you are using a mesh collider because you have to and you have no choice, primitive colliders don't work out for you. They make them convex. I know you can also get artists, they will do that. They'll create a collider or a mesh that has a lot fewer faces, and that will be able to be used as a mesh collider there for your project. So that's something that could be very useful. And then use layer masks. In the examples I gave, I did not use any layer masks, but you can actually use layer masks to determine what to interact with or not. So definitely look into that. Alright, those questions will be for another time. Thank you for paying attention, and make sure you complete the assignment associated with this video. Until next time, bye.